Welcome to the deep dive. This is where we take source materials and, well, really dig into them to pull out the key insights just for you.
hmm
You want to get up to speed quickly, really understand a topic, but without getting totally overwhelmed by all the details.
Yeah, cut through the noise.
Exactly. So today we're tackling something that's really fundamental to a lot of modern tech. Fast approximate nearest neighbor search. ANNS for short.
Right, and it might sound a bit technical, but think about it. Image search, music recommendations, finding similar products online. ANNS is often working behind the scenes.
It's everywhere, isn't it? And it's crucial because, well, the amount of data out there is just exploding. We need efficient ways to handle it all.
Absolutely. Searching through billions, literally billions of items,
Yeah.
finding the exact match perfectly every time. That's often just too slow.
Way too slow. So a really good approximation, something very close but delivered like instantly. That's often the goal.
Yeah.
It's much more useful in practice.
Precisely. And for this deep dive, our source is excerpts from a research paper. It's titled Fast Approximate Nearest Neighbor Search with the Navigating Spreading Out Graph.
Okay, the Navigating Spreading Out Graph, or NSG. Sounds interesting.
It is. The paper really dives into the core problem. How do you find similar stuff efficiently in these massive data sets? And it proposes this NSG as a novel way to do it.
Got it. So our mission today is to understand why searching for similar things is so tricky at scale, and then explore how this NSG approach tries to crack that nut.
Okay, let's jump in. What's the fundamental difficulty here? Finding neighbors sounds simple enough.
Well, at the basic level, it's nearest neighbor search, NNS. You have a query item, say a photo you just took, and you want to find the most similar photo in a huge database.
Or maybe the top 5 most similar.
Exactly, that's K nearest neighbors, finding the K closest ones. But doing this perfectly, finding the absolute mathematically proven nearest neighbors, that gets incredibly expensive, computationally speaking.
Especially when the data is complex, right? Like lots of features describing each item. Precisely. High-dimensional data. Think about describing an image not just by color, but by textures, shapes, objects present. Hundreds or thousands of dimensions.
Ah, the infamous curse of dimensionality. I've heard that term. Why does that make search so much harder?
Yeah, it's a real challenge. In these high-dimensional spaces, our intuitive sense of distance kind of breaks down. Everything starts to seem, well, roughly equidistant from everything else.
Huh. So it's harder to tell what's truly close.
Exactly. Traditional methods that try to carve up the space, like putting things in boxes or indexing regions, they become less effective. The boundaries get fuzzy. Algorithms often end up having to check way more points than you'd ideally want, even points that are actually quite far away, just to be sure.
Okay, that makes sense. So perfect is too slow and too hard, especially with complex data. That leads us to the approximate part, ANNS. What's the trade-off we're making?
It's a classic speed versus accuracy trade-off. With ANNS, we're willing to accept that we might not find the absolute single closest item, or maybe we miss one of the top K occasionally.
But in return,
In return, we get our answers much, much faster, often orders of magnitude faster. And for most applications, like recommendations or web search, slightly approximate but super fast is exactly what you need.
right. How do you measure how good an approximation is?
A common metric is precision. Basically, you look at the K neighbors the ANNS algorithm gives you, and you check how many of them are actually among the true, correct top K neighbors.
So high precision means you're getting mostly correct answers.
Yep. You want high precision, ideally close to 100%, but you also want very low search time. That's the balancing act.
Okay. Now, the paper mentions some existing ways people have tried to solve this ANNS problem before NSG came along. Can you give us a quick rundown?
Sure. Broadly, there are non-graph-based methods. Think things like tree-based structures, KD trees, R-star trees. They try to recursively partition the data space.
Like drawing boxes within boxes.
Sort of, yeah.
Yeah.
Then there are hashing-based methods like locality-sensitive hashing, LSH. The idea there is to have similar items likely end up in the same hash bucket. And also quantization-based methods like product quantization or PQ. These try to compress the data, the features, into shorter code so you can compare them much faster.
So different ways to organize or compress the data to avoid checking everything. Smart. But where do they stumble, especially with these huge high-dimensional data sets?
Well, the paper argues that many of these run into trouble again with that curse of dimensionality.
It keeps coming back.
It does.
Yeah.
In very high dimensions, the way they partition space or create those compressed codes might not capture the true similarity structure effectively anymore. You might still need to check lots of distant points or buckets to get good accuracy.
I see. So that opens the door for a different approach.
Exactly. And that's where graph-based methods come in. They become really promising, especially in recent years.
Okay, graph-based ANNS. How does that work? What's the core idea?
It's actually quite intuitive. You represent your entire data set as a big network, a graph. Each data point, each image, each song fingerprint is a node. And you draw connections, edges, between nodes that are similar or close to each other based on their features.
So similar items are linked together in the graph.
Precisely. Then, when you get a query, say, you want to find images similar to a new one, you start somewhere in the graph and basically walk along the edges, trying to navigate towards nodes that are increasingly similar to your query.
Ah, okay. It's like exploring pathways of similarity. The paper mentioned a specific search strategy called greedy best first search. How does that fit in?
Right, that's a very common way to search these graphs. Algorithm 1 in the paper describes it. Imagine you're at a certain node, data point, in the graph. You look at all its direct neighbors, all the points connected to it by an edge.
Okay.
You calculate how similar each of those neighbors is to your query. Then you simply jump to the neighbor that looks the most promising, the one that's closest to your query so far.
And you just keep doing that, always jumping to the best looking neighbor.
Yep. You repeat the process. Look at the neighbors of your new location, pick the best one relative to the query, jump there. The hope is that by always making the locally optimal move, you'll quickly converge towards the true nearest neighbors in the graph.
Okay, that makes sense. For that to be efficient, though, you'd want two things, right? First, the actual path to the nearest neighbor in the graph shouldn't be too long.
Exactly. Short search paths are crucial.
And second, at each step, you probably don't want to have, like, thousands of neighbors to check. The number of connections from each node, the out degree, should be reasonably small.
Spot on. Low average out degree and short paths. Those are really the keys to fast graph search. If nodes have too many connections, checking all neighbors at each step becomes slow. If the paths are long and winding, it takes too many steps.
So the challenge is building a graph that has both those properties. The paper then goes through a bunch of existing graph types people have tried. Delaunay graphs, KNN graphs, RNG, MSNet, NSW, HNSW, wow, lots of acronyms.
Yeah, there's quite a zoo of graph structures out there. Each tries to strike a different balance.
What are the main trade-offs they run into?
Well, some, like theoretical Delaunay graphs, have this nice property called monotonicity. You're guaranteed to always find a path where each step gets you closer to the target. But
There's always a but.
always. In high dimensions, these Delaunay graphs get incredibly dense. Too many edges, so searching is slow. Things like KNN graphs connecting each point to its k-nearest neighbors are simpler, but can also be dense and need lots of memory.
Yeah.
Others, like relative neighborhood graphs, RNG, try to be sparser, fewer edges, but then you might lose that guaranteed monotonic path, making search less direct.
Right, maybe not enough connections.
Exactly. MSNets guarantee the path, but are apparently very costly to build. Then you have the really popular ones like NSW and especially HNSW hierarchical navigable small world graphs.
HNSW comes up a lot. They're good, right?
They are very effective, often state-of-the-art. They try to approximate desirable properties like navigability and small world characteristics. But HNSW, with its multiple layers, can use quite a bit of memory, which can be an issue for truly enormous datasets.
Memory usage, okay. And others. Randomized neighborhood graphs.
They can have good search time complexity, theoretically, but building them, the indexing complexity can be quite high. So you see the pattern, it's this constant tension. Search speed, accuracy, memory footprint, and construction time. Getting all four right is hard.
Definitely like a balancing act. Which brings us finally to the navigating spreading out graph, NSG, the main focus of the paper. How does it try to break this cycle? What's its core idea?
So NSG is proposed as a way to explicitly tackle these trade-offs head-on. The authors say they designed it with four specific goals in mind.
Okay, what are they? First, ensure connectivity you need to be able to reach any data point from any other point in the graph. Obvious but crucial. Second, lower the average out degree. Keep the number of neighbors per node small for faster steps. Third, shorten the search path, make navigation efficient. And fourth, reduce the index size, keep the memory requirements low.
Connectivity, low degree, short path, small index. Sounds like the dream team for ANNS graphs. How do they actually build a graph like that? The paper mentions a theoretical foundation first, something called MRNG.
Right. Before NSG itself, they introduced the monotonic relative neighborhood graph, MRNG. This is kind of the theoretical ideal they're aiming for. MRNG is designed to be a monotonic search network.
Meaning it has that property where there's always a path that gets progressively closer.
Exactly. It guarantees a monotonic path exists between any two nodes. And importantly, they show MRNG has potentially near logarithmic search complexity that's very fast and, critically, a constant maximum degree.
Constant max degree, meaning the number of connections per node doesn't explode as the dataset gets bigger.
Precisely.
Yeah.
Which is theoretically fantastic for scalability.
Okay, that sounds amazing. Near logarithmic search, constant degree. Why not just use MRNG then? What's the catch?
The catch. The paper points out that actually constructing the perfect MRNG using the most direct method has a very high indexing complexity. It would just take too long to build for the kinds of massive data sets we're talking about.
Okay, so MRNG is the beautiful theory, but too slow to build in practice.
Pretty much. And that's where NSG comes in. NSG is designed as a practical approximation of MRNG. It tries to capture those great search properties, low-degree short paths, but with a much more efficient construction process.
Got it. NSG is the buildable version. How do they actually build it? Algorithm 2 in the paper lays it out.
Yeah, it's a multi-step process. First, they start by building a quick and dirty approximate KNN graph. Just get some initial neighborhood information.
Okay, a starting point.
Then they pick one special node called the navigating node. Think of it like an approximate center point or medoid of the whole dataset.
A central hub.
Kind of, yeah. The idea is that paths starting from this node might be good proxies for efficient paths generally. So for every other node in the dataset, they do a search on the initial KNN graph. Starting from that navigating node, trying to reach the target node, they collect candidates along these paths.
So they're finding potential neighbors by exploring from this central point.
Exactly. It helps find relevant connections that might be missed by just looking locally. They combine these path-based candidates with the node's original KNN neighbors. Now, from this combined pool of potential neighbors, they don't just connect to all of them.
Right, they want low out degree.
Precisely. They use a selection strategy inspired by MRNG's logic to pick at most M neighbors, where M is a parameter you set. This keeps the graph sparse.
But wait, if you limit connections like that, couldn't you end up with parts of the graph disconnected, like islands?
Good point. That's the final step.
Yeah.
Because pruning edges might break connectivity, they run a check. They do a depth-first search, DFS, starting from the navigating node to find all reachable points. If any points are missed, they add back just enough edges from a spanning tree, also rooted at the navigating node, to connect everything up again.
Ah, okay. So find good candidate neighbors using the navigating node, select a limited number smartly, and then patch up any accidental disconnections.
That's the essence of it. The goal is to get graph properties like MRNG efficient search, low degree, small size, but build it much faster.
All right, so the theory and construction seem clever. How does it actually perform in practice? The paper shows a lot of experimental comparisons.
Yeah, they tested NSG against a whole suite of other methods, FLAN, ANOI, phase, HNSW, KGraph, and others on standard benchmark datasets like SIFT-T1M, GIC1M, millions of data points.
And what did they find?
A key finding, first off, was that graph-based methods in general, including NSG, tended to outperform the non-graph methods significantly in the trade-off between search speed and accuracy or precision.
So graphs really do seem better for this.
For these kinds of data sets, the evidence suggests yes. They generally need fewer distance calculations to reach the same level of precision.
Okay. And how did NSG stack up against the other graph methods, like the popular HNSW?
This is where NSG really shone, according to the paper. It often achieved a better balance. Specifically, NSG frequently had a smaller index size, meaning it used less memory compared to other top graph methods like HNSW, KGraph, or Afana.
Smaller memory footprint is a big plus for large scale.
Definitely. And in terms of performance, NSG often outperformed the others, especially when they push for very high precision, like getting 95% or 98% of the true neighbors correct.
So better performance at high accuracy and smaller index.
That's what the results indicated on these datasets. The paper also notes that NSG's advantage seemed to grow on datasets with higher local intrinsic dimensionality, basically. Datasets where the structure is more complex locally.
Interesting. What about the time needed to build the NSG graph itself? Was it competitive?
The indexing time for NSG was generally reported as being faster than many other high-performance graph methods like KGraph or Afana, though maybe not as fast as HNSW in some cases, and typically slower than non-graph methods like FACE's quantization.
So maybe a moderate build time, but leading to faster search and smaller size?
That seems to be the trade-off profile, yeah. For applications where search speed and memory are paramount, Maybe a slightly longer offline build time is perfectly acceptable.
The paper also mentions something about HNSW or FANG sometimes missing direct edges to the actual nearest neighbors. How does NSG address that?
They argue that NSG's construction, specifically the step where it explicitly considers the initial KNN neighbors and then uses its selection strategy, is better at preserving these crucial nearest neighbor links compared to some iterative refinement methods used elsewhere, which might prune them away. Keeping those direct links helps ensure shorter, more accurate search paths.
Okay. And they really push the scale, right? Testing on hundreds of millions, even billions of points.
They did. On a 100 million point dataset, Deep 100 Beaver, NSG showed strong performance against Phase, even when Phase was using a GPU. And then there was the test with Taobao, Alibaba's e-commerce platform.
A billion scale, real world test.
Exactly. They implemented a distributed version of NSG across multiple machines to handle the sheer volume. The results were impressive. NSG met the strict response time requirements, we're talking milliseconds for real user searches, and significantly outperformed the existing IVFPQ baseline system they were using.
Wow. So it works in the wild at massive scale.
It seems so. They also mentioned that building or updating the index daily was feasible even at that scale, which is crucial for dynamic data like product inventories.
That's pretty compelling evidence for the practicality of the approach. Okay, let's try to wrap this up. If you had to summarize the key takeaways from this deep dive into NSG, what would they be?
I think the main point is that NSG offers a really effective and well-engineered approach to ANNS. It seems particularly strong when you need high accuracy and need to handle very large data sets efficiently, both in terms of search speed and memory usage.
And its success comes from that careful design, right? Balancing those four aspects.
Yeah.
Connectivity, low degree, short paths, and small index size.
Exactly. By explicitly targeting those four goals, using the navigating node concept and the MRG-inspired edge selection, it seems to manage that tricky balancing act better than many previous methods, at least on the datasets tested.
Plus, the real-world validation at Taobao really underscores its potential impact.
Absolutely. Seeing academic research translate into a core component of a major search engine like that is significant.
It really makes you think, doesn't it? The core principles here, finding efficient paths through vast amounts of interconnected information based on similarity. How could that apply elsewhere, beyond just image search or product recs?
That's a great question. Maybe in drug discovery, finding similar molecular structures, or analyzing complex network data in social sciences or biology. Anywhere you have massive data sets and need to find reloaded entities quickly.
It's this fundamental problem of navigating complexity. It forces you to consider those trade-offs: speed, accuracy, memory. How much precision do you really need for a given task? It certainly encourages looking deeper into these graph indexing techniques.
Definitely food for thought. The innovation in this space is pretty incredible.
Well, thanks so much for guiding us through this. It's been fascinating to unpack the NSG approach.
My pleasure. It's a cool piece of work.
And thank you, our listener, for joining us for this deep dive. We hope it's given you some valuable insights into the challenges and solutions in the world of fast approximate nearest neighbor search.